Hi everybody, we are Power of SNNs, and we're a group focused on exploring neural networks. Our group consists of three principal members: Akil, that's me, my partner Nilufar, and the all-important pink board. So why should we care about neural networks?
Neural networks are important. They can learn new things, detect and track objects, learn to generate speech, and most important of all, distinguish cats and dogs. Let's say you want to run object detection on your smartphone. If you use a full precision convolutional neural network, the model would probably not fit into your phone's memory. Even if it does, it would be extremely slow and it will kill your battery quickly. That's why quantized neural networks are introduced for edge devices. These are networks that do not have full precision and need less computation and storage resources. Quantized neural networks usually run on 8 bits. In an extreme case, namely the binary neural network, they need only a single bit, which can be either 1 or -1. It's true that BNNs are faster than full precision neural networks because they take up less memory and are less compute intensive, but they still consume too much power and they cause some loss in accuracy. So, how are we supposed to run neural networks efficiently on edge devices? Well, worry not. Spiking neural networks are here to save the day. Since they work with spikes, if there is not an input spike, the computation unit can remain idle and save energy.
Spiking neural networks theoretically have much greater power efficiency and could serve to be super useful for edge devices. However, SNNs have rarely been compared with other efficient networks to see if they are good in practice. Our goal was to put the SNN up against a similar BNN to see how well it fared. But instantly we ran into problems. First was the problem of properly generating inputs. Should we encode the input via frequency of the spikes or through magnitude of the spikes? How do we turn these spikes into current? How do we turn these currents into voltages? To address these issues, we turned to a lot of reading and prior research and managed to make a current generator for our neurons. But when we took our existing current generator and tried to move forward to implementation, we noticed that a lot of the other networks on the internet had a really simple input current. They were just using the intensity of the pixel as an input function. So we decided to follow suit and change our input currents to that as well. Now that we had a valid input, we should construct a neuron, right? So we built a neuron from the equations found in our prior research, and our results were, well, not that great. But we managed to get over that hurdle and fix our neuron to make it as close to accurate as possible.
Well, now that we have our input spike and our working neuron, we just have to choose our network architecture. That seems easy, right? No, that's really wrong. First, we wanted to use a high accuracy model that was offered by NengoDL. But this model had a problem. The 5 layers made it huge enough not to fit into a pink board. So we decided to change the architecture, make it 3 layers, and then use that. Well, that was not easy either. Tweaking neural network parameters is a really hard thing, and trying to make a 3 layer network work properly was not fruitful. So we decided to switch to a new model. We switched to a 2 layer network that was only comprised of LIF neurons. This network could do feature extraction and not classification. Therefore, it was not a complete network. But we decided to use this one since we could fit it easier on the FPGA. Our results show that a BNN performs better on software than an SNN, and that is because an SNN has to do multiple rounds of execution to get an acceptable error rate. We also observed that if we run a BNN on a pink board using only software, it runs extremely slower than running it on the hardware.
And that's our results. Thanks for watching.